it is, and at least you know the argument why it is correct. Okay. So second, the change should be sufficient size, should be large enough, okay, so that estimates are accurate and stable. Okay, so here, okay, the size of the chain, okay, again, has something to do with the sampling process. Okay, if your sampling process is more efficient, then you don't need that many samples. Okay, you probably need like just a couple of thousand. Remember, like in the previous examples in the textbook, we use only 2,000, right? Normally, we only generate 2,000 samples, and the result is already pretty nice. That's because, if I remember, we use PUA sampling technique, and that sampling technique is very powerful. Okay, but if you use for example, even for general metropolis algorithm, okay, it is really not that powerful because, well, you can obviously imagine that was the first sampling technique that was proposed. Obviously, after so many years, there are many sampling techniques that have been proposed to improve metropolis algorithm. Okay, so yeah, in doing Bayesian data analysis, I mean, we normally just generate tens of thousands, about 10,000, okay, to even 20,000 samples, okay, for each chain. Okay, but again, that depends on which type of sampling technique we are using. Okay, so the change should be the change should be generated efficiently with as few steps as possible, so not to exceed our patience or computing power. Okay, but nowadays, okay, because the computer has become so powerful, okay, this is normally not going to be an issue. Okay, if you try to generate, for example, 2,000 samples by using the example in the textbook, okay, you will find that, yeah, it takes some time, but just a couple of seconds, okay, really is not going to be an issue. Okay, that's because the current personal computer is so powerful. It was so powerful. I mean, back to remember this sampling technique was first proposed in the early 90s. At that time, the computer, the computing power of the early 90 computer is actually weaker than most of the smartphone that you have in your pocket. Okay, so yeah, I mean, obviously there's we need to take into account the computing power, but this is normally not the issue. I mean, for the current computer technology. Okay, so if you want to know how representativeness, the mcmc chain that you generate, okay, so you can use visual examination of the trajectory, and also you can consider certain numerical description of the convergence. Okay, the reason I want to cover this part is just to show you, I mean, some of those things. I mean, so first, a visual examination. Okay, when you generate samples by using mcmc, any of the mcmc sampling techniques. Okay, first let me repeat. Okay, this is this is for a different textbook, so they use a different way to generate a different sampling technique and to generate the result. And this is based on R. So I to our if you remember like our Python like textbook, okay, we only has like the upper left figure and the lower right figure. You may not think like upper left figure. You say, oh, upper left figure doesn't look like we have that that one. But if I show you another one, it should be more obvious to you, right? The upper left figure. You remember, like in the textbook, I mean, every time we generate like a posterior, we have something similar to upper left figure, right? That shows the trajectory of the parameter value. Okay, so you see, it actually represents like how the sample, the parameters are jumping from one value to another. Okay, remember it's a random walk, right? So it goes up and down. Okay, it goes up and down. So, but you may wonder like how come, this one doesn't look like you can see there are three chains, right? There are three chains in the upper left figure, right? But you feel like, well, this upper left figure, these three chains do not mix so well like this one, right? So why? It was because, take a look at the iteration. This is like the first 500 iterations. Okay, so in the first 500 iterations, you can see these three chains actually initialized at the different locations, right? And they just got started, so they gradually converge to the area that has higher posterior value, okay, which is like somewhere close to 0.8, right? But you can see, before like 400, 500 iterations, these three chains, they are still very far apart from each other, right? And that's nature. And think about that. Remember when we draw our result that looks like this, we actually, if I remember, I told you we got rid of the first 500 iterations, right? We use those first 500 iterations to tune our sampling process, right? Why do we need to tune it? It's because if you don't get rid of those earlier sampling process, they are going to be affected by the initial value, okay? And so the upper left corner indicates that the parameter value, okay, or the trajectory of of different chains, okay. If your chains are representative, most likely these different chains, even though they start from different locations, they will mix very well. Okay, they will mix very well, and if you still remember, in the Python version, okay, we have upper left figure and the lower right figure. The lower right figure is the kernel function. Okay, basically, it's kind of like if you try to look at this figure, okay, in turn 90 degree, you turn this figure 90 degree and calculate like how many the frequency of each values from 0 to 1. Okay, and the one with the more frequent visit, okay, will has a higher value, something like this. Okay, so you create a kernel function like this. Okay, so we have these two, but we didn't have the lower left, this shrink factor, and we didn't have this autocorrelation. Okay, for the so the upper left one and the lower right one, I mean, should be relatively easy for you guys to understand. For lower left one, it is a special, it's called German factor, okay, or shrink factor, okay. Basically, okay, we are looking at I mean, if this value is reduced to close to 1, okay, that means like your chain is generating very well, okay. But since this derivation takes some mathematical skill, okay, so we'll skip that. And even doing Bayesian data analysis, they just say, oh, this has to be close to 1, okay. If it's larger than 1.1, you have an issue. But just that, okay. It didn't actually talk more about this, okay. So I will skip this part. But the upper right one, I would like to spend some time to talk about it, okay? Because like the upper right one, okay, the correlation, okay, has something to do with the effective sample size. Remember, in our like summary, parameter summary, we show like for example, like after we generate like a posterior for some parameters, we show like maybe like the average, mean. We show the mean, we show the standard deviation, and we show like maybe 94% HPD, the range, right? And we have a field that tells you effective sample size, right? I told you guys like don't worry about that, okay? We will talk about that later. So that's now is the time that I would like to talk about that. But before we talk about that's equivalent to this ESS. Okay, so this ESS has something to do with autocorrelation. Okay, so I will have to tell you guys what the autocorrelation is in order to tell you what the ESS is. Okay, so well it's. So I will skip this. Yeah, this one talks about like the figure on the lower left corner. So I will skip that. Okay, and yeah, autocorrelation. The autocorrelation is a measure of clumpiness. Okay. It's simply the correlation of the chain values with the chain values k steps ahead. Okay, so there is a different autocorrelation for each choice of k. So autocorrelation, okay, if you look at this lag represent that k value. Okay, this lag represent the k value. So what does that mean? Okay, let me show you this figure. Yeah, maybe it's let's take 10 minutes break. When we come back, we'll discuss this autocorrelation. Okay.